The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Good. So before we start, do you have any questions on what we did before? Okay, so we have discussed that black hole can be considered as a thermal object, and that actually black holes obeys the standard law of thermodynamics. And now we also mentioned that it's a natural question to ask whether black hole should be considered as ordinary quantum mechanical object. And so this is related to the issue of information paradox. So, but if one disregards this information paradox, which I think now have a very good, in principle have a reasonable resolution, which we will talk about later. But if we do treat the black hole as an ordinary quantum mechanical object, then there are actually very important implications. So one implication is this called the holographic principle. So holographic principle by itself is in some sense a rather heuristic concept at the moment, and I will also not to make it, and I will also only give you a very heuristic discussion, and it's possible to make it a little bit more rigorous, but I will do it at a rather heuristic level, just to give you a feeling that there's something profound going on in quantum gravity because of the black holes, So let's consider an isolated system of mass, say E, and say entropy S0, say in asymptotic flat space-time. Okay. And let me also denote A as the area of the smallest sphere that, say, encloses the system. Okay, and also let me introduce, let MA be the mass of the black hole of the same horizon area. Yeah, say with black hole with horizon area A. Okay. So in GR, anything which is sufficiently massive will eventually collapse to form a black hole. Because of that, So we must have E is smaller than MA. Okay. So we must have E. So whatever energy you can put in this region surrounded by area A must be smaller than the mass of a black hole, which you can put in that region. Okay? Because otherwise, if we have more mass, then we will already be a black hole. Yeah, say equal. So now let's suppose E is smaller than MA. So we can now suppose E is smaller than MA. Now we can add this amount of energy, say MA minus E amount of energy to the system. Okay, suppose we can do that, keep A fixed. Okay. Suppose we can do that, keep A fixed. And then this will reach a black hole mass. Then the final system will have a. Then the final system will be will have a black hole. We'll have the black hole. We'll have the energy given by MA, and that object must be a black hole because because that's the black hole with the same horizon area. Okay. So that's because of this process also tells you that the black hole entropy must greater than the S0, the initial entropy of this system, plus the S prime. S prime is the entropy of added energy. Okay. So just because of the second law of thermodynamics, your entropy should not decrease. So the final, so you add this amount of energy so that to MA, so then you will precisely form a black hole of the mass MA, and with the horizon area A, and but this black hole entropy should be greater than S0 plus the entropy you added. This is from the second law of thermodynamics. Okay. So then that means your initial entropy must be smaller than the black hole entropy. Okay? Must be smaller than A divided by 4 h bar g Newton. Okay? So this argument tells you that the maximal entropy inside a region bounded by area A is given by okay? Yes?
So we're keeping A fixed at extra entropy to the system?
Yeah.
So in that case, why we don't have such a term?
Sorry?
So you said well, we want to keep A fixed.
Yes.
Will that add extra entropy to the system?
Yes.
So according to the second law of thermodynamics, why we claim that the entropy of black hole is greater than or equal than S naught plus S.
Yeah.
Okay, it's added energy.
Yeah, because this is the energy of added
But
energy. Yeah.
how about the actual energy that might be introduced by keeping A fixed, like because it's not a.
Yeah, whatever it is, whatever it is. Suppose you can keep A fixed. Then whatever things you added to that total entropy must be smaller than the black entropy because black hole is a fellow state.
You said it's an isolated system, so with that, how can you make sure that A is fixed? Why is it?
Oh, yeah. I'm just saying we are doing a thought experiment. Imagine you can do this by keeping A fixed. Yeah, just say you just put stuff in into this region so that stuff does not come out. Yeah, just you have some region A. Maybe let me do it here. You have some region A. And there's some mass inside here. There's some energy stuff inside here. So this is region A. And then you just keep putting stuff in. Just keep putting stuff in so that those things don't come out of A, don't come out of this region. That's what this means.
Then A is not a smallest sphere. Then A is not a smallest sphere too.
A is what?
Not the smallest sphere that encloses the system. So that's required. It's not a.
No, A is not the smallest sphere increased system. A just. Maybe I should call it just A is area of a sphere. Yeah. Sorry. Thanks. So just enough A to be a sphere that encloses the system. Yeah. Yeah. Sorry. I should not put the smallest there, for some reason. No. A should not be smallest. Just A is any sphere, just some sphere which encloses the region. Okay, yes?
So it seems that this argument implicitly assumes that in order to add entropy, that sort of corresponds to adding some amount of energy. But is it possible to add entropy to the system without adding energy to the system?
Oh, you can. You can. They just make it even more. Whatever it is, this is a fellow state. So the basic assumption of this is that if you can put stuff inside this region, whatever is inside, the assumption says the maximal stuff you can put inside the region is a black hole with the horizon area.
Well, I guess what I'm confused about is that it seems that I certainly believe when you say that you can't have a certain amount of energy in an area, but I'm not sure why you can't have a certain amount of entropy in an area if energy and entropy are not.
No, we are not making that assumption. The entropy is just a consequence of that. This is a final state entropy. And the final state entropy is always larger than the entropy of your initial state.
Okay, sure.
Yeah, entropy is a derived. This equation is not assumption, it's derived.
Fine. Okay.
Yeah, the assumption is that the black hole is the maximal, it's the most massive object you can put inside this region.
Sure, I see.
Yeah.
But you can have a less massive object with more than that entropy. You can have a less massive object with entropy that is more than that value inside the same region.
This is ruled out by this. Once you get this equation, then you don't ask about the mass. It just any entropy must be smaller than this value. Any other questions? Yes?
How do we keep track of the area? I mean, doesn't space begin to get warped with the horizon approach?
Right, so that's why I say this is a little bit heuristic argument. And that's why I say this is a heuristic argument, yeah. Yeah, indeed, you have to be a little bit more careful about that. Say if you the key thing is about the area. And this order 1 coefficient, one maybe have to think about it when you include the quantum corrections, etc., the back reaction, etc. Yeah, but the key thing is the area. The black hole must be proportional to the area.
Well, is this duration based on assumption that the area of the horizon of a black hole is only based on the mass?
Yeah. So there, let me say again, there's 2 nature of this argument. The first nature of the argument is the maximal energy you can put inside the region is a black hole whose horizon area is given by the area of this region.
This is assumption.
Yeah, this is assumption. Yeah, because we know in the GR, any sufficiently massive thing will collapse to form a black hole. Yeah, and if you have more mass, then the horizon area will be outside, and then you will be outside this area. You can no longer keep this A fixed. Yeah, so that's the first assumption. So with that assumption, then just follows from the second law of thermodynamics, because this is whatever the entropy of the matter inside, then this is whatever the initial entropy you do of the energy you need to put it in to make it into a black hole, and then that must be smaller than the entropy of the final state, which is the entropy of the black hole.
But my question is that by keeping A fixed, you might introduce actual entropy into the system.
Yeah, it doesn't matter as far as the black hole is a final entropy state. What you are saying is that there might be some other things here. It's fine. That does not change the direction of this.
That entropy might be negative. I'm not sure. Just
no, whatever it is, this is my initial. So that's why this is inequality here. This is not equality, inequality, and we are just using the second law of thermodynamics. This is your initial state entropy. This is my final state entropy. This must be greater than that. We are not asking the specific process. We are not asking the specific process. Yeah, just the final state has to be greater than initial state. Good? Okay, so now let's see what we can try to go a little bit further from here. So now let's recall. So now we really treat the black hole as a quantum statistical object. So now recall definition of entropy. In quantum statistical physics. Okay. So if you say I have some system, and the state of that system is described by some density operator or density matrix, and then the entropy of that system is just given by this formula. Just given by this formula. Okay. In particular, for a system with n-dimensional Hilbert space, okay. So this is the n-dimensional Hilbert space. Okay, this is a dimension of the Hilbert space. That S max is log n. So the maximal possible entropy you can have is log n. Okay, is this fact familiar to you? So you can convince yourself the maximal entropy is realized when rho is just given by 1 over n times the identity matrix. Okay, and so this is the density matrix which have low information, because every state plays the same role, and this state then you can plug in here and give you log n, and the maximum entropy means you have minimal information. Okay, and that is the state with the minimal information. And you can also just prove yourself using some algebra. But this is a physical argument for this. So now, if you compare with these two formula, then we can draw a conclusion is that so let me add a word called effective dimension of the Hilbert space for a system inside a region of area A is bounded by log n must be smaller than A h bar Gn. Okay? So that tells you, so whatever you can put inside this region of area A, that's the maximum entropy you can have. So, and if you have n degrees freedom, then the maximum entropy you can have for this n degrees freedom is log n. Then that tells you that log n must be smaller than this. Okay, smaller or equal to that. And so let me write this in terms of the. So this can also for h bar n is also a Planck length square. So it's also 4 times the Planck length square.
Sorry, for this part, usually Hilbert space can be even infinite.
Yeah, let me say that. So that's why we need effective. So now let me make some remarks. Now let me make some remarks. So 0 remarks is that for a system of n spins, say n spin half particle. So when I say spins, I always mean spin half. Then the dimension of the Hilbert space is 2 to the power n. Okay? Just remind you. But the dimension of H, the Hilbert space. So normally I use script H to denote the Hilbert space for a single harmonic oscillator. So the simplest system is spin. Then the next simplest system is essentially a harmonic oscillator. And even for a single harmonic oscillator, and the dimension of H is infinite. Okay? And then you ask what I'm talking about here. Because here I say the Hilbert space should be smaller than that. But, okay, so even for a single harmonic oscillator, the Hilbert space is infinite. But for a quantum mechanical system, for a quantum system, with a finite number of degrees freedom, by finite number of degrees freedom, for example, you can interpret as, for example, finite number of harmonic oscillators. Okay, the dimension of the Hilbert space below some finite energy scale, energy is always finite. Okay, it's always finite. And so that's why I use the word effective there. And because normally we all consider the finite energy. Yeah, because the system will have finite energy, and then you have effective, you have a finite dimensional Hilbert space. Okay? So this equation is not that crazy. So in typical physical systems, even for harmonic oscillators, both for spin or harmonic oscillators, essentially number of degrees freedom is of order log n. Yeah, it's the n is the effective dimension of your Hilbert space. Okay. Yeah, this is obvious from the spin. Okay, this is also obvious if you have a harmonic oscillator. So each harmonic oscillator is finitely excited, and then again, roughly the log n is the number of harmonic oscillators. Okay. So because of this, we can also write this equation as the number of degrees freedom of any quantum gravity system inside the region A should be smaller than, should be bounded by the area of that region. Okay? So this bound is certainly violated in non-gravitational systems. Okay? Because in non-gravitational systems whose number of degrees freedom and thus the log n, the log of your dimension of your Hilbert space, is proportional to the volume rather than area. So when the region is big enough, then you are guaranteed to violate this bound, because of course the volume grows faster than the area if you have a sufficiently larger region. So for example, consider just a lattice of spins. Say three-dimensional lattice of spins of lattice spacing A. Say of lattice spacing A. Okay. Then the total number of spins. Then is given by volume divided by A cube. Okay. So this is essentially the number of degrees of freedom. And then this is given by A, the area, divided by A squared times L divided by A. And this can be much, much greater than A divided by Planck square, Planck length square, for L sufficiently large, okay? L large enough. So if you have a long gravitational system, then this bound can be easily violated. In particular, this equation can also be violated because the dimension of the Hilbert space, then in this case would be 2 to the power a cube. And similarly, so the maximal entropy would be, say, V divided by a cube log 2 because it's a spin tube system, spin half system. So this can be larger than the entropy of a black hole. So it's key that we can see the gravitational systems, okay? Only in gravitational systems you have this remarkable feature that if you things will collapse, okay? Things will collapse, and then you will have this upper limit provided by the black hole. Yes.
So in the real world, every system is a gravitational system.
Yeah.
So this is just, in some sense, this is not actually correct in the real world.
Yeah, but you need this L to be large enough.
I see.
Yeah. Yes.
So, right, in the real world, this bound has to be obeyed by systems. So does that put some like bounds on UFT UV completions? So in the real world, this bound has to be obeyed by everything.
Yeah.
So does that put some kind of restrictions on like QFT UV completion? Because we usually say it's infinite density of degrees of freedom.
No, because the UV completion over QFT is provided by gravity.
For any QFT? I just mean like a scalar field.
Then that's not a theory of gravity.
Right, but if you have a scalar field in a space-time which has GR in it,
Yeah.
but is otherwise like flat.
Yeah, then the then the gravity will provide the UV completion of that scalar field. Yeah. Right. I was going to say something else, but I forgot.
What about the ones that are UV complete? What about the theories that are UV complete, at least formally?
Sorry, say it again?
The QFTs that are UV complete.
Yeah, they are still limited by gravity. Okay. Yeah, the gravity will still provide something. Because QFT have infinite number of degrees of freedom. Yeah, so example of this, for example, you can think a classroom, say full of photons, and then you can calculate entropy. Again, that entropy will be proportional to the volume. So if you make the classroom big enough, then that will violate this bound. But it's a simple exercise for you to do yourself, that if you put the classroom at the finite temperature photon, then when the room is big enough, there's always a radius that will collapse from a black hole before this bound is violated. Okay, I think maybe I have this problem in the piece. I forgot whether I have it or not. Yeah, you can do this simple exercise yourself. Yeah, just imagine you have a box of photons at any non-zero temperature T, and then when you put the box big enough, then at a certain point this whole box of photons will collapse from a black hole, and that's when it form and that's within to make this bound to be satisfied. So what this means, that if you have gravity, the quantum gravity leads to a huge reduction of number of degrees freedom. Okay? It's really bounded by your area.
Now, in previous argument, what if you have a conformal field theory? And so this also apply to conformal field theory, we don't need to have a UV completion.
No, Yeah, as I was answering Pavel before, if you have a conformal field theory just by itself, then there's no bound. Then there's no bound. But if you couple this conformal field theory to gravity, then at sufficiently high energy, and then the degrees of freedom of this conformal field theory must be reduced.
But if you just have a conformal field theory, then there's no bound.
No bound, yeah. Yeah, but you can ask what happens if we couple a conformal field theory to gravity, not even conformal field theory, just any quantum field theory. Because any quantum field theory have infinite number of degrees of freedom, and the number of degrees of freedom is also proportional to the volume. And if you couple it to gravity, then this reduction must happen. This reduction must happen. Okay? So now if we take a small leap of faith, so we already have taken some leap of faith, but let's take one more step or leap of faith. Then you can formulate something called a holographic principle. So given that the number of degrees of freedom inside the region is always bounded by the area, and this area actually have a very nice way, its area in the unit of Planck's length. It looks like you have a minimal length, minimal area, which is a Planck square length, and just the area divided by that give you the total number of degrees of freedom. Okay. So if you try to extrapolate a little bit further, then we have a so-called holographic principle. It said in quantum gravity, a region of boundary area A can be fully described by no more than. So essentially, it's just very a H bar Hn is a degrees freedom. In other words, 1 degree of freedom per Planck area. Okay. So this is the just a rough formulation of the holographic principle. So what we just said, it just highlights a point we made earlier, is that even though naively from dimensional analysis, that the quantum gravity is only operating, say, at Planck scale, say at Planck mass or Planck length, etc. But we see that the black hole actually brings the quantum gravity really to macroscopic level, okay? Because these are the really macroscopic statements can apply to regions of arbitrary size, but somehow they are limited by constraint of quantum gravity, okay? So this is the a remarkable manifestation of the quantum effect. Any questions on this? Yes?
What's so special about two-dimensional surfaces? Can it be generalized to...
Oh, yeah, this you can generalize to any dimension. Just always call dimension 2. So if you live in 5 dimension, then becomes 3 dimension. Yeah, it's always call dimension 1 in the spatial region. Because the black hole, just area of the black hole is always called dimension 1 in terms of spatial. Yeah.
What can you say, 10-dimensional space, 3 sphere, and then it's...
Yeah, 10-dimensional space, then naively, this would be constrained by 8-dimensional surface. Yeah. Yeah, just no matter what dimension, it's always constrained by the surface, not constrained by the volume. No matter in what dimension. Other questions?
I just have a question back to there.
Yeah.
So it seems like we are like constraining a system, a quantum theory, that its number of states for a given energy must grow slower than some, because we must be lower than some finite energy, right?
Yeah.
The number of states must be below certain.
Yeah, essentially what we said earlier is that if you are in the theory of quantum gravity, there's a cutoff on the maximal energy you can have. And there's a cutoff also on the maximal energy you can have, because otherwise you form a black hole. And then that cutoff translates into the statement about the entropy and into the number of degrees freedom.
Yes, I mean.
Because much easier, yeah.
I mean, for example, we have first we start with a simple theory, then maybe for example, add, for example, standard model, then we add supersymmetry, then the energy spectrum, the limiting energy that is there, but the number of Hilbert state is more. And we can keep doing things like that.
Yeah.
But we can't, because it must be below this value.
Yeah, but you see, there's something about the volume here. You have to talk about the within some region. Of course, abstractly, you can put some degree. Yeah, maybe I'm not getting your question.
I just say, naively, I would think we can just, for example, say the energy bound is here, and below this, how many states we could have?
No. This is not the direct in terms of entropy energy bound. This is in the end is the bound on the long body with freedom you can put inside a region. If you put too many degrees freedom inside the region, then you need to enlarge the region. Yeah, just say it's look like the number of degrees freedom is incompressible, something like that.
Okay, I also have a question regarding back to your earlier.
Yeah.
So I still don't understand. Shouldn't the isolated system means also including the machinery to do these things?
No, I'm just saying you start with an isolated system, then you can add something to that isolated system.
What about we take matters out of the black hole? This equality will.
No, you take it. No, that isolated system does not have to be a black hole. It can be anything. It just can be anything.
So if we instead putting energy inside, we take energy out.
Yeah, you take it.
Entropy will decrease.
Yeah, just take entropy out. Yeah. Then this bound will be even more satisfied.
I have a question there that the degree of freedom.
Yeah.
I mean log of degree of freedom.
No. N is the dimension of the Hilbert space.
Oh.
N is the dimension of the Hilbert space. That's what I call the N here.
Yes.
N dimension of the Hilbert space.
But the degree of freedom is.
Typically, the number of the dimension of the Hilbert space is exponential of the number of degrees of freedom.
Oh, okay.
Just look at here.
Oh, I see.
Just look at here. Yeah. Any other questions? Okay.
If we have a quantum field theory, it has a certain vacuum energy, right? And then if you now consider that to be the vacuum energy and you expand it, at some point it will actually collapse into a black hole. So if you take the vacuum energy to be that predicted by Q of t, then for the universe it would not work. Even theoretically. I mean, I know the cosmological constant is 120 orders less, but.
Yeah, that's a little bit tricky because so the vacuum energy will make it into, say, depending on whether vacuum energy is positive or negative, will make it into de Sitter or anti-de Sitter. Then you try to see whether, it depends on details.
But if you go big enough, it's gonna collapse.
No, not necessarily. I'm just saying that you have to formulate a little bit differently. You're talking about a particular state of certain energy to couple to gravity. then you just take that state, couple to gravity to see what you get. Yeah, then ask questions from there. Yeah. Good. So now let's move to a new topic. Still is in the preparation to go to the duality, but we need another piece of important intuition in order to fully appreciate the duality. And this piece of intuition is Nagian series. Yeah, let me call it Nagian matrix series. Okay. So now we want to look at now we try to look at the hint for holographic duality from the field theory side. Okay, from the field theory side. So far we have been talking about the hint for holography from the gravity side, and now we look at it from the field theory side to see actually from field theory side there's also some hints to relate a non-gravity system to a gravity system. Okay, so let's start with QCD. So QCD is a SU3 gauge theory. Plus quarks. Okay. So we can. So let me just write down its Lagrangian. Okay, so this F describes the gluon field, and this psi describes the quarks. Okay, so this F is built out of the standard partial mu A mu minus partial nu A mu minus A mu A mu, and A mu, each gauge field is a 3×3 Hermitian matrix. Okay, so these are 3×3 Hermitian matrix. So this is using the matrix notation. So F is also a matrix. So there's a trace here. Okay, Hermitian matrix. And the TA is just the generators of SU3. Okay? So it doesn't matter if you don't know QCD. It doesn't matter if you have not seen QCD before. The only thing matters is just to remember that QCD is a series of matrices. QCD is a series of 3×3 matrices. Okay, so the gluon field is a 3×3 matrices. It's described by matrices. So of course, one of the remarkable thing about QCD. What's the most remarkable thing about QCD? Do you know? Yeah, that's one. And what other remarkable thing about the QCD? Yeah, it's related to that. Yeah, confinement is also related to that. It just one of the most remarkable thing about QCD is still not solvable. And the reason it's not solvable is because when you go to low energies, the coupling becomes strong, then we don't know how to deal with it. Okay. So we still don't know how to calculate it from first principle. Of course, we can put it on the computer, but just from the in terms of theoretical understanding, it's hard. So in 1974, so this is old problem. So starting in 1974, starting in 1971, people already tried to solve it. So in 1974, so the big problem of this thing is that in quantum field theory, normally we do expansions, okay? Say we find some starting point. So in physics, that we always do. We find a starting point, which can be solved. Then we expand around that starting point. And that starting point is often a free theory. And then we expand upon the free theory. So the difficult thing about this theory is that first it's hard, when you go to low energies, first it's hard to find a starting point. And the second is that there's nothing to expand because there's no small parameters. Okay, there's no small parameters. When you need to expand, you always need a small parameter. So in 1974, Hooft came up with a very nice idea. He said, this is SU3. He said, let's just take the number of color. Which is n equal to 3 as a parameter. So even though in real life he said there are only there's only three type of colors, but let's imagine we treat it as a free parameter, okay? So this just implies, say you promote the gauge field to m by n matrices, m by n Hermitian matrices, okay? Okay? You say, let's just treat this by in terms of m by n matrices. And then let's consider n go to infinity limit. Okay, so let's consider n go to infinity limit. So he reasoned if n go to infinity limit is sufficiently simple, then maybe we can solve that limit and then do 1 over n expansion. 1 over n then is a small parameter, then we can treat 1 over n as a small parameter and then do 1 over n expansion. Okay? So that's the rough idea. And then you get a small parameter because 1 over n. So in real life, n will be 3, so 1 over 3. It's not very small, but it's at least smaller than 1. Okay, so this turns out to be an ingenious idea. But unfortunately, QCD still cannot be solved this way. But there's a surprise. So it's still a QCD you cannot solve this way. Even n go to infinite limit turns out to be too hard. But there's a surprise. It turns out this 1 over n expansion gives you a string theory. Okay? So I will now explain this, okay? I will now explain this. So there's a byproduct of his large n expansion is that you find that this actually, such a gauge theory is actually secretly a string theory. So the key is that these fields are matrices, okay? So the key reason this emerges is because we are working with fields which are matrices. So I will to illustrate this, I will not do the QCD. It's a little bit complicated. I will just do a simple scalar field theory. Okay. So I will just do a simple scalar field theory as an illustration. So let's consider the following theory. Okay. So this G is still a coupling constant. For what we do, it's actually convenient to put it in the front. Of course, you can rescale it. I'm sure you can rescale it to put it here, which is the normal place. But I put it in the front, just like what we normally do also for QCD. Okay, so this G is a coupling constant which we put in the front. And then each phi, again, I take it to be an n by n Hermitian matrix. Phi x, each one is a matrix A, B, so I have 2 index. So this is n by n Hermitian matrix. Yeah, n by n Hermitian matrix. So which means that phi AB equal to star equal to phi BA. Okay. So there's a difference between the upper and lower indices. Okay. So I can write it more explicit in terms of components. So just to give you, in case some of you are not familiar with this kind of matrix kind of field theory, so let me just also write it in terms of components. So write it in terms of components. It's 1/2 partial mu phi AB, then partial mu phi BA, then plus 1/4 phi AB, phi BC, phi CA, phi CD, phi DA. Okay? Okay, so this is the, so just having writing down the explicit using components. So this L, by definition, is invariant under in addition to the usual translation, rotation symmetries, etc. It has also internal symmetry under UN, global symmetry. Okay, so say phi x goes to U, phi x U dagger for any U, any constant as UN matrix. Okay. So this series is invariant under, so this is obvious from here because of this trace. So this is invariant under this. Okay. So let me just make some remarks before proceed to talk about the features of this series. Let me just make some quick remark. Zero. He said this is a series of n-squared scalar fields. Okay. So if this is intuitive to you, then this just means you have many fields coupled together in some specific way. Okay. And also, we don't have to consider Hermitian matrices. To consider Hermitian matrices just for simplicity, one can also consider other type of matrices. For example, real, say, symmetric matrix. Say it's real symmetric or anti-symmetric matrices. So in those cases, if you consider, say, real matrices, then symmetric or anti-symmetric matrix, in that case, this global symmetry becomes SON, okay, rather than UN. So in here, this U is a global symmetry, just U has to be constant, cannot depend on X. You see it from here, cannot depend on X. But you can also introduce gauge fields to make this UN symmetry local. Okay. So I will not do it now, but this will be important a little bit later. So later we will indeed make it into a local gauge symmetry. But for now, let me just consider this simple example, okay? Because I don't want to introduce too many fields, etc. So any questions regarding the setup of this theory? Yes?
Can you explain that last point one more time? So what do you mean that how does introducing gauge fields make the symmetry local?
Yeah, you have to take 8, 3, 2, 4 to know that. But the simple way to explain it, yeah, there's no simple way to explain it. Yeah, just say, let me just explain the statement. If you introduce some gauge field, then you can make this U to be some arbitrary function of X rather than a constant. Okay. So that's the statement of a local. Yeah. Just say I can generalize this theory so that this symmetry become a local, become a symmetry so that U can have arbitrary X dependence, can have arbitrary space-time dependence. Yeah. So right now U must be a constant. Any other questions? Good. Okay, so now let's just try to do perturbation theory. Think G squared small. Try to do perturbation theory. Okay? So the first thing you do, of course, is to write down the Feynman rules. Say first you have to look at the propagator. Okay, look at the propagator. So you can essentially, you are all field theory expert. So just by looking at that Lagrangian, then you can immediately write down this propagator. We can just write down x minus y. Okay, so whatever propagator, whatever space-time dependence, let me just call it x minus y. But also there's a non-trivial index structure. First, there's also G squared. Okay, because there's a prefactor 1 over G squared. So when you invert the kinetic term, there's a G squared. But the index structure is at AB, BA. So that A must contract with D, and B must be the same as C. So that means you have delta AD and the delta CB, BC. Okay? Okay, because in the Lagrangian, only those fields are paired. So the propagator must have this structure. So similarly, we can write down so there's a 4-particle interaction vertex. So each particle have 2 index. So this is AB, CD, EF. Oh yeah, right. Sorry. Let me add one more, and then I can denote this diagrammatically just as ABCD. Okay. It just denote this diagrammatically as the propagator, which is wavy line ABCD. Okay. And now also we have this quartic interaction vertices, which involving 4 fields. So each field have 2 index because AB. So AB, CD, EF, GH. But this is not arbitrary interaction. They have contracted in the interaction. They contract in a specific way. So you get 1 over G squared because of all factor G squared, and then you have delta BC. delta dE, delta Fg, delta HA. Okay, because they have to be contracted. Okay, I should better write it as AB this way, AB. Okay, so AB, B contract with C, D contract with E, E contract with G, H contract with A. So this gives you a matrix product. So just like that. Okay.
So in the propagator, you exchanges A and D.
AB. Yeah, let me just call DC. That's right. Okay. So this is a Feynman rule. So now you can start calculating. Okay. So if you have calculated this for a while, then you find this is a little bit tedious. With all these indices, it's quite annoying. And but Tuhov is a smart. Tuhov was a smart fellow. So he said, let me find a way so that I don't have to keep track of all these indices. Okay. Then he invented a very nice way. So this is called double line notation. So first, this propagator, A, B, C, D, since that A is contracted with D, C is contracted with B separately, he said, let's just write it as a double line. But since there's a difference between the upper and the lower indices, so let's define a direction for this double line. So this should be so let's define the direction to go from the upper index to the lower index. Then you will have AB, then you have D, then CB. Okay, because for C, it's upper to lower index. We go from CD. Okay. So now you don't have to worry about this this thing anymore because it's automatically taken care of by this notation. Similarly, this one is also automatically taken care of because each one, if you replace it by the double line notation, then you just make it A, B, then B is equal to C, B equal to here, C equal to C, D equal to D, and A equal to A. Okay, and then we have G square. Here you have G square. Okay. So once you draw the double line notation, so let me also draw the arrow. Once you have a double line notation, then all those annoying deltas, they're automatically taken care of. Okay.
On the left side, it's really delta CD. C is on the top of B.
Sorry, which one?
The left, yes, there's 4 vertices.
Here?
Yes, C is on the top.
Delta.
Yeah, if you write this arrow.
Oh, okay. Delta BC, that's right. BC. Good, good, good. So now let us give you some examples of using this diagram to calculate things. And also try to calculate the independence because eventually we want to take a large n limit, okay? So we want to keep track of the independence. Yes?
The 4-point coupling, does that come from the commutator in the F menu and the gauge theory?
No, I just wrote it down by myself.
Okay, so it's an additional thing. Okay.
Yeah,
So you
it's
just
a
postulate it.
it's arbitrary just arbitrary field theory. Yeah, just an example. Okay, so now let's start calculating. You have already have the Feynman rule. What you wait for? So let's just calculate. So the first thing, let's look at the vacuum energy. Okay, so that's the first thing to calculate. So what's the vacuum energy? The vacuum energy is all the diagrams. It's a summation of all the diagrams without external lags. Okay. Yeah, let's just. So the simplest diagram is just with one vertex. Okay, so this is the simplest diagram. But now, so if you do lambda phi 4 theory, then that will be the end of the story. Okay? You just contract of them. But now, the matrix, because we are contracting matrices, okay? So this is like contracting 4 matrices. When you're contracting matrices, but matrices don't commute. So actually there's a difference. So you should convince yourself. There's a difference which I actually connect these two from which I connect these two and these two. Okay? Because this corresponding to I connect the neighboring ones, and this one I connect the diagonal ones. And the order actually matters. Okay, the order actually matters. Because matrices don't commute. So if I call this A and B, and A not equal to B. Because the matrices don't commute. Okay? So now let's do the n counting. So do the n counting is actually much simpler. We use this double line notation. So let's now use the double line notation. Because all this n, so when you do the contractions, you have all these indices. You sum over all those indices. When you sum all those indices, you get some factors of n. So that's how n will come into this theory. And but double line notation makes the constraint all manifest. So the contraction will be automatic. You don't have to worry about all those deltas. So let's just do that. Let's draw this 4-point vertex. For this one, we just contracting neighboring ones. For this one, we do the same thing. We contract non-neighboring ones. Yeah, I did not draw very well. So. Okay. So this one should be contracted with this one. This one should be contracted with that one, and this one contract with this one is contracted with that. Okay? So there's some intersection. So now let's count the n. Okay? So now here is the key. Each loop corresponding to a contracted indices. Okay? So for example, in here, this is already A, and then if you contract these two, then you sum over this A when you calculate the propagator, and then that gives you a factor of n. So each closed loop essentially gives you a factor of n. Okay? It's just because you contract. Yeah. So there's 3 loops here, 3 contracted loops. So this gives you n cubed. Okay? And if you look at the g-square dependence, so you have 2 propagators here. You have 2 propagators. Each propagator gives you a g square. Then you have 1 vertex. Each vertex gives you a 1 over g square. So you have g squared. Okay? So now let's look at this one. This one, let's just follow this line. You should also draw the arrow because the arrow should follow. Okay? I did not draw the arrow, but the arrow should all follow. Okay, the arrow should be consistent. Similarly here. So here, if you go around, you find there's only a single contracted line. So this is only a factor of n. Of course, g squared dependence is the same. So you have g squared. Okay. So now you already see the difference between these two diagrams, and one is proportional to n, one is proportional to n cubed. So A, diagram A can be drawn on the plane. We are drawing it on the plane without crossing. Without crossing lines. So we call it a planar diagram. And B cannot be drawn on the plane without crossing lines. So we call non-planar diagram. Okay. So let's do one more step. So let's do one more diagram. So let's do one more diagram. Okay. So next order, you just get two. Next order vacuum diagram without any external lag, you have two vertices. Okay. So you can connect this way. Okay, so this is one diagram. You can also have planar, non-planar diagram. Yeah, let me just draw the straight line rather than the wavy line, just to save trouble. You can, for example, you can draw like this. So this is a non-planar diagram. Okay. So now I'll give you an exercise. Today, when you go home, turn those into a double line diagrams. Then you should find yourself that this is n to the power 4. Yeah, maybe I should do this. Yeah, let me do this one for you. So let me just do this one quickly for you. But I will not draw the arrows just to save time. Okay. So this one, you count how many contracted lines. 1, 2, 3, 4. So this gives you n4th behavior. And this I will not do it now. You do it yourself. So also if you count the g dependence, this gives you g to the power 4. And this gives you n squared, g squared. Not g to the power 4. Is it g to the power 4? Maybe I'm counting wrong. 1, 2, 3, 4. 4 propagators is g squared. Yeah, g to the power 4. Yeah. Yes?
So in general, the more crossings, will that decrease n?
Yeah, that's right. Okay. So now you can just continue with 3 vertices, with 4 vertices, etc. But of course, the smart fellows will not stop. And they ask, can I find some rules in doing this? Say, how do you get the general n counting? And whether does the all long planar diagram was the same, or one need to classify them further? Okay, so these are the obvious questions. So let me just tell you some observations. Then I will close for today. So the first observation So just from those examples, let me just draw some observations. Observation 1. So this one requires a little bit ingenuity. It said even A and B, so this A and B, they cannot be drawn on the plane. They cannot be drawn on the plane without crossing lines. But A and B can be drawn on the torus without crossing lines. Okay? So now let me show it to you. So what is a torus? So we can draw a torus on the plane like follows. So we draw a square. Then we identify this side with that side. Identify this side with that side. Then this gives us a torus. Okay? So because when you do that, then give you a cylinder, and then you do that again, then give you a torus. Okay? So, but on the plane, just simple identification. So let's try to see this diagram. Now let me show this diagram can be drawn on the torus without crossing. Because the vertex is like this. We want to contract this guy with that guy and that guy with that guy, right? Non-labeling ones. But now I can just go up. And now this is identified with here. Then I can come back here. Can go here, come back here. Okay? So this is contracted. And I don't have to cross lines. Yes? Good. Similarly, let me do that one. Yeah, that one maybe I will let you to do it yourself. Yeah, do the so this is A. This is oh no, this is not A and B. This is B and D. Let me call this B. This is let me call it C and D. So A and C are planar diagrams, and B and D are non-planar diagrams. Okay. So this is B. So try to do yourself the D. So essentially you have two vertices. How to make that non-planar diagram to be planar on the on this torus when you identify here with there, there, with there. Okay? So this is observation 1. Actually, let me just do it for you. So we connect because I need to it's better I have this example to make my second point. So now I need to connect this to that guy, but I can do it by going up. This guy can go here, and then go there. Similar thing, okay? And then this is I can connect them without crossing lines. So this is the observation 1. So now the observation 2. Again, it's a little bit ingenious, but maybe slightly easier if you have done it long enough. For all the A to D, the following rule is true. The power of n is equal to number of faces. So this one we call, so even though there cannot be the cross lines on the plane, but we can actually straighten them out on the torus, okay? So here we can straighten them out on the torus. So the second observation is the power of n is the number of faces in each diagram after we straighten it out. Okay, first let's look at this diagram. This is a planar diagram. So there's one face, there's two faces, And then there's a face outside because it's a whole plane. So there's 3 faces. So this is n cubed. And the B on the torus, there's only 1 face because each region is connected to each other. Okay? So there's only 1 face. You see the power n. So now in C, you have 1 face, you have 2 face, you have 3 face, you have 4 face. Okay, so this is n to the power 4. And for this one, you have 1 face corresponding to here. And then you easily convince yourself everything outside this region, they're connected through the identification. So you get n squared. Okay, you get n squared. So these 2 observations. So let me stop here. And then from here, you can figure out the general rules for everything. Mm.